Let's now look at heaps. So recall that our goal is to implement a priority queue. In a priority queue, we have a sequence of jobs that keeps entering the system. Each job has a priority. Whenever we are ready to schedule a job to execute, we must pick up not the latest job or the earliest job that we got, but the job which currently has the highest priority among the waiting jobs. Therefore, we need an operation called delete max, which will search for the highest priority job among those that are pending and schedule it next. And we obviously have an insert operation which adds these jobs dynamically as they arrive. So we saw last time that a linear structure will not allow us to simultaneously optimize these two. Okay, we end up with an order n operation for delete max or an order n operation for insert. Then we saw a trivial two-dimensional array which gives us an n root n solution. That is a root n operation for each of these. So over n operations, it's order n root n. But we said that we will find a much better data structure using a tree of a special type called a heap. So the heap is going to be a balanced tree whose height is logarithmic in the size. That is, if I have n nodes in the tree, the height, that is the number of edges from the root to any leaf, will be log n. And with this, it will turn out that both insert and delete max are proportional to log n. And therefore, processing n jobs will take time n log n as opposed to n root n for the array or n squared for the linear representation. We also said that this heap in principle is flexible and can grow as large as we want, so we don't have to fix in advance the size of the heap that we need to keep. So let's start looking first at what a heap is. So a binary tree is a tree where we have a root and every node has 0, 1 or 2 children. So binary trees in general can have arbitrary shapes. Okay, so we could have binary trees which look like this, where the root has 1 child, this has 2 children, or it could look even more skewed in one direction. Okay, so binary trees can have very strange shapes. But a heap is a binary tree which has a very specific shape, where we fill up the tree nodes or we add the tree nodes in a specific order. So first we start at the root, then we must add the left child of the root, then the right child, and this way keep going level by level, left to right. So we add this node, then we add this node, then we add this node. So once I know how many nodes are there in the tree, I know precisely what the shape is, right? So the shape is fixed. Right? So that is the first feature of a heap, that if I have a heap with n nodes, then the shape of the tree is deterministically fixed by this rule that the n nodes must be inserted top to bottom, left to right. Okay. Then we have a value property. Right? So the value property says that, okay, so what is happening in the tree is that we have nodes and each node is a value. So whenever I see a node with value v1 which has children v2 and v3, okay, then what we want is this is bigger than or equal to v2 and bigger than or equal to v3, right? So among these 3 nodes, the largest one must be v1. So this is what is called the max heap property. So this is a local property. It just tells us at every node, look at that node, look at the 2 children, the node must be bigger than its 2 children. So here is an example of a heap with 4 nodes. So first, because it is 4 nodes, every 4 node heap will have this shape, because the first node will be the root, the second node will be the root's left child, third node will be the right child, and the fourth node will start a new level. Then moreover, we can check the heap property, right? So we see that 24 is bigger than 11, 24 is bigger than 7. So this is a valid node for a heap property. 11 is bigger than 10, there is no right child, so this is a valid heap. There is no child of 7 at all, so by trivially this is a valid heap node, and 10 is a valid heap node for the same reason. Okay, so every leaf node which has no children always satisfies the heap property. Okay. So once we have a leaf node, there is nothing to check. So here is another heap. This one has 7 nodes, so again the shape is fixed, and again you can check that this is bigger than 11 and 7, 11 is bigger than 10 and 5, and 7 is bigger than 6 and 5, and the rest are all leaf nodes, so there is no problem. Right? So these are 2 examples of heaps. So what is an example of something that is not a heap? So here we have something which is not a heap because the structure is wrong. Right? So we said that you can't leave holes. You must go top to bottom, left to right. So there should be some node here before you add the node on the right. Right? So where is this node? This node is missing. So this structure is not right. For the same reason, this structure is also not correct, because we have here something which is missing a node at this level and we started a new level. Right? So both of these are not heaps for structural reasons. Here on the other hand, we have something which is a valid structure. In fact, we saw a heap before which has this structure. The problem is with this node. Okay? So we want 7 to be bigger than 8 and 5, but this is of course not the case. 7 is not bigger than 8, 7 is smaller than 8. Right? So this node 8 actually violates the heap property. So something can fail to be a heap either because the tree structure is wrong or because at some node the heap property is violated. In this case, the node that violates the heap property is 7 because one of its children is actually bigger than the node itself. So now we have to implement these two operations on heaps, insert and delete max. So let's see how it works. So first let's insert 12. So insert 12 means I have to add a value to the heap. So the first thing when I add a value to the heap is I must expand the tree. So where do I put this node? So this is now fixed because we know that heaps can only grow and shrink in a particular way. So I must add the new node, okay, left to right, top to bottom. So in this case, if I go left to right, top to bottom, right, I come to this point. Now I can't add anything more. So it must come at the next level. Right? So the first thing is that this is where the new node must come to contain 12. Now, if I put 12 into this position, the problem is that I might not have the heap property satisfied. In this case, you can see that the heap property actually fails right here because 12 is bigger than its parent. Right? So 10 violates the heap property. But notice that this can only happen above. Okay? So what I mean is that when you insert something, it's a leaf. Right? So since 12 is a leaf, it cannot fail the heap property below 12 because there is no child below 12. If at all the property fails, it is because the parent of the new node has a value which is too small. So there is a simple way to fix this locally at least, and that is to exchange these two. Right? So I exchange this 12 and 10, and now I fix the problem here. But now I've changed the value at this point, so I have to look at this configuration to see whether what I moved the 12 into violates the heap property or not. And here again you can see that there is a problem because 12 is still bigger than its parent. So then I exchange that, so now I've exchanged this. Now in the process what has happened is that 12 has gone from here to here, okay? And now the first thing we have to convince ourselves is that the heap that the local heap property that we just fixed doesn't need any further fixing. In other words, we have to guarantee that there is no problem at the other side between 12 and 5, okay? And this cannot happen because we originally had 11, 5 and something here. We knew that 11 was bigger than 5 and it was bigger than this something. Then we did an exchange and we brought a 12 here. Right? So if at all the problem is only between 11 and 12, and since if there is a violation, 12 is bigger than 11, that's why there is a violation, but 11 is known to be bigger than the other side. So if I move 12 to the top of this 3-node structure, it cannot be smaller than the other side because the root currently is already bigger than the other side, and the only reason I move 12 up is because it is still bigger than that side. Okay? So then in a nutshell, when I do an upward swap like this, I can be sure that I don't have to look on the other side. Right? I just keep looking up. So now I brought 12 up to this point. So now I need to check whether there is any further violation, and it turns out that 12 is smaller than 24, so I can stop. Right? So this was the result of inserting 12 into this heap. Now I can insert a new node 33 just to convince ourselves we know what to do. So as before, if I insert 33, so this was the result of the heap after 12, and now I've inserted a 33 here. Okay, so it has to be to the right because that's the next node in the structure, and I put the value, but it violates the heap property between 11 and 33, so I swap it up. And then again I have a violation here, so I swap it up again. Again I have a violation here, so I swap it up again. And now I have reached the root, so actually it's become the biggest node, and now I can stop. Okay. So how long does this take? So every time we do an insert, we start at a leaf node, a new leaf node that we create, and we walk up to the root. Right? So the worst case of such a thing will depend on the worst case height of the tree. We have to bound the height of the tree. The height of the tree, by definition, if I have a tree like this, okay, so the height of the tree is the longest such path. The length of the longest path from the root to the node. Okay? So you can either count in terms of number of edges or in number of vertices. If it's vertices, this one will be 4. If it is edges, it will be 3. Doesn't really matter. But the point is that the longer such path will determine the complexity, because the longer the path, the more times I may need to swap on the way up. So what can we say about the height of a heap? Okay. So the first thing to notice is that in a heap, because of the way that we have done it, okay, so at the root node we have at level 0, if we call this level 0, okay, we have exactly one node. At level 1, at most we have 2 nodes. Okay, so we can write this as 2 to the power 0. This is 2 to the power 1. Now, of course, now each of these will have 1, so it will double, right? So at every level, the number of nodes doubles because each of the previous level has 2 children at most. So we have 2 square. So in this way, we have number of nodes at level 0 is 2 to the power 0. At level 1 is 2 to the power 1. At any level I is 2 to the power I. Okay. So if we have k levels, then the levels are 0, 1 up to k minus 1. From what we have just said, that is 2 to the 0 plus 2 to the 1 plus 2 to the k. 2 to the k minus 1 it should be solved. Okay. So it will be 2 to the 0 plus 2 to the 1 plus 2 to the k minus 1. Okay. Now this, and one way to think about this, this is a binary number with k ones. Right? So binary number with k ones is just 2 to the power k minus 1. In other words, if I fill up a binary tree for k levels, I will have at most 2 to the k minus 1 nodes. Right? So therefore the number of nodes is exponential in the number of levels. So therefore if I have the number of nodes, then the number of levels must be logarithmic in that. Okay? And the number of levels is what determines the length of the longest path. And therefore insert in any heap will take time log of n, because there is every path is going to be guaranteed to be of height log n. Okay, so the other operation that we need to implement for a priority queue is to delete the maximum. Right? So the first question is, where is the maximum in a heap? So the claim is that the maximum is always at the root. Why is that? Because if I start anywhere, I know that among any 3 nodes, the maximum is at the top. Right? So if I look at 33, for example, 33 is bigger than 24 and 7. Right? But inductively, I know that 24 must be the biggest node in this subtree and 7 must be the biggest node in this subtree. So therefore 33 is bigger than both, so it must be the biggest node overall in this entire tree. Okay? So the model is the maximum value is always at the root. Right? So now the question is, if the maximum value is at the root, right, how do we remove it from the tree efficiently? So let's say we remove the maximum value. So then this leaves us with a hole, right? We don't have any value at the root now. At the same time, because we have removed the value, we have reduced the number of values in the tree by 1. But we said that the structure of the tree is fixed. If we reduce by 1, we cannot remove the root. We must remove the last node going on this left to right, top to bottom order. So we must in fact remove the node here. This node has to go. Right? So now we have a value which is homeless, it doesn't have a node to belong to, and we have a home which is empty. Right? So what we will do is we will move this 11 to the root. Right? Now unfortunately, because we have disturbed the heap order by doing this, taking some arbitrary node from a leaf and moving it to the root, we don't know whether we have the heap property satisfied or not. Now the only place where a heap property can be violated is at the root, because everywhere else the local neighborhood was not touched by this operation. Right? The only other place where a neighborhood was touched was here, but all we did was remove a node. If you remove a leaf, then it cannot violate a heap property, because for the upper node it was already bigger than both these children. Right? So this is okay. So the only place we could have a violation is here, and indeed we do, right? Because 11 and 24 are in the wrong order. So we will start now restoring the heap property downwards. When we insert it, we do it upwards. So we'll start here and look at this, and then we will look at both directions, and we'll take the bigger one of the two and move it up. Okay, so we swap with the largest child. Suppose, for instance, that this had been not 7 but 17. Okay, then what would have happened if we had moved 17 up is we would have got 17, 11 and 24. Right? And this would not have fixed the heap property, because this would still be wrong. Right? So we must take the bigger of the two and move it up, because among these three, the biggest value must be at the top. That's the definition of the max heap property. Right? So we exchange the 11 and the 24. So 24 goes up to the root, and then 11 has come in this direction. So we must again check whether this part, which has now been disturbed, satisfies the heap property, and of course in this case it doesn't, because 11 and 12 are not in the correct thing. So again, among these three, I have to take the maximum value up. So I take the 12 up and move the 11 down. Okay? And now I have to check this section whether this heap property is satisfied. Here it is satisfied, and now I install. Okay? So in delete max, I start from the root and I walk downwards. Okay? So supposing we do this again, okay? Then I remove 24, right? And then I move the 10 from the last leaf to the top. Then I again have to fix this problem, right? So I exchange the 10 and the 12. Then I have to look at this and fix this problem. So the biggest of these three is 11. I fix the 10 and the 11 and I get it. Right? So now by making sure that I take the biggest one up, again I don't walk down the other direction. So I'm always walking down a single path. Right? So once again, just like insert, the cost is proportional to the height. And since we know that in a heap the height is logarithmic, delete max is also an order log n operation. Right? So what we have done is we have shown that a heap actually does both delete max and insert in log n time. Okay? Now another very nice property about heaps is that we don't actually need to maintain a very complex tree-like structure. We can actually do heaps in arrays. To do this, we observe that we can canonically number all the nodes in a heap. Right? We start numbering the root by 0. The first node we fill below the root by 1, the other child by 2, and so on. So I have a numbering 0, 1, 2. So I can actually represent this heap as an array which has indices 0, 1, 2, and so on. Okay? Now in this, the claim is that if I am at a position I, okay, so if I have some position I, then the children of this are 2i plus 1 and 2i plus 2. You can check this everywhere. So therefore, if I want to actually go to a heap and ask something about the heap property, then I will just look at position I, and then I will jump ahead to position 2i plus 1 and 2i plus 2. Right? So completely using the array alone, within the array, I can look up the children of a node, and by inverting this operation, if I look at j minus 1 by 2 and take the floor of that, okay, then I will come backwards. Right? So if the child is 2i plus 1, 2i plus 2, then the parent is j minus 1 by 2, and then it might be fractional, so take the integer part. So floor means take the integer part of j minus 1 by 2. Right? So this is not j minus half. Okay? So read it as j minus 1 the whole by 2. Right? So for example, for 12, j minus 1 is 11. Okay? 11 by 2 is 5.5. Floor of that is 5. So the parent of 12 is 5. Okay? So you can check that this is formed. So therefore, I can now do all my heap manipulation within an array, which is very convenient. I just have to write an array, and then whenever I do these operations which involve walking up or down the heap, I just use this 2i plus 1, 2i plus 2 formula, or I use this floor of j minus 1 by 2 formula. So how do we start this whole process off? How do we build a heap from a given set of values? Right? So a very naive strategy would work as follows. I am given a set of values, n values by x1 to xn. So I start with an empty heap, right? And then I insert x1. So I have a heap of size 1. Then I insert x2. So now I have a heap of size 2 and so on. So I do n inserts, right? And each insert takes log n time at most. Actually, it will take less time. It will take log I time if I have inserted I items so far. But let's take log n as an upper bound, right? So overall, if I insert these n elements, I will build the heap also in n log n time. Now, in fact, it turns out that there is a better way to do this. Okay? So if I look at any array, I can think of this as a heap. Right? I can just imagine that it is ordered, because every array has a heap interpretation. I can imagine that this is how the array looks if I think of it as a heap. Of course, it doesn't satisfy the heap property, but this is how it would look if I arrange it as a heap. Now in this, anything which is at the leaf level doesn't need to be checked because it has no children. All leaves trivially satisfy the heap property. Right? So I need to start fixing things only at the previous level, so I walk backwards. So I come here, right, and at x3 I fix the heap property with respect to its children. Then at x2 I fix the property with respect to its children. In the process, something will move up and down, but only one level. Then I will come to x1 and I will fix its problem. Now this might involve two levels. Right? So for each level k minus 1, k minus 2, so leaves are at level k. At level k minus 1, k minus 2 on up to the root, we fix the heap property. So as we go up, fixing the heap property means walking down like we did for delete max, walking down to the leaf. Okay? So each level we go up, the length of this path increases by 1. But because the levels double as we go down, they halve as we go up. So the number of nodes for which we have to check this extra length path goes down by a factor of 2. Okay? So now if you do the analysis, which we are not going to do exactly, okay, it turns out that in this process, the number of updates you need to make a heap is actually only order n. Right? So if we use this bottom-up heapification, then it will be an order n procedure. So just to get a better picture of what's going on, so let's assume that we had 15 elements in our list, right, and we actually drew it out like this. And the claim is that these n by 2 nodes, okay, which is roughly half, it's actually 8 out of 15, already satisfy the heap property, so there's nothing to be done. So then I go one level up and I fix these, right? And when I fix these, I have to do it for 4 nodes, and each of them, the repair will involve 1 swap at most, or no swaps. Right? Worst case, it will all be 1 swap. Okay? Then I will go up one level, and now for each of these nodes, I will have to possibly go down 2 paths of length 2. Right? So each of them will involve a height 2 repair, that is 2 steps of thing, but then now from 4 nodes I have gone to 2 nodes. Right? So there are only half as many nodes which require only 1 step more. Okay? And then finally when I go to the root, I might have to do a kind of fix which involves swapping down to the last leaf, so 3 swaps, but there's only 1 node which does this. Okay? So therefore, since there's this trade-off that the number of nodes to be fixed is halving and the length is only increasing by 1, it turns out that this whole operation takes only order n time. Okay. So to summarize, what we have seen is that heaps implement priority queues using special balanced trees. In these trees, both insert and delete max are logarithmic. We can use this bottom-up heapify to actually build a heap in order n time. And what is most useful is that this heap can actually be manipulated very simply as an array. Now, one thing which we can do is to invert the heap condition. So we can say that whenever we see v1, v2 and v3, we want v1 to be smaller than both v2 and v3. Right? So this is what is called a min heap. What we have been doing so far is a max heap. So sometimes we want to keep track of the smallest priority and remove the smallest priority item. Okay, just think of how, for example, you rank people in an exam, right? So if somebody in a competitive exam, the smaller the rank, the higher the priority. So if you have rank 1, then you have highest priority. So in some situations, it is natural to think of smaller numbers as higher priority. So you don't have to do anything very much. You just have to change the heap rule to be minimum. Okay, so that each node is smaller than its 2 children, and then everything will work exactly as we have done so far. Okay, so you have 2 types of heaps. You have max heaps and you have min heaps. And all that differs in max heaps and min heaps is the heap condition on the nodes, and the correspondingly whether the operation you implement is delete min or delete max.